This video showcases our work at IROS 2023, titled Pyramid Semantic Graph-Based Global Point Cloud Registration with Low Overlap. The work is capable of achieving accurate global registration even with low overlap, given 2-point clouds without initial poses. The code for this project has been open-sourced on GitHub, and we welcome everyone to give it a try. In recent years, the use of maximum clique theory to assist in removing outliers has become popular for achieving robust global point cloud registration with low overlap. The registration process can be divided into two parts. In the front end, we obtain the initial correspondences through a point cloud matching algorithm, and in the back end, we construct a compatibility graph and solve the maximum clique to remove outliers. Then, we estimate the transformation for the remaining matching relationships. As shown in the figure, for point clouds with low overlap, the outlier ratio may be high, such as 99.2%. However, after the maximum clique filtering, the outlier ratio will be significantly reduced. We commonly refer to this outlier removal strategy as maximum clique Inlier selection. The first step of this strategy is to construct a compatibility graph. In this graph, each correspondence represents a vertex, and there is an edge between two vertices if they pass the compatibility test. Secondly, we identify the most probable set of inliers by finding the maximum clique. Specifically, a clique is a subgraph where each vertex is connected to every other vertex. Inliers generally form at least one of the maximal cliques. Furthermore, the maximum clique represents the most likely correct clique. Here, I would like to provide a simple example of the compatibility test. In the given figure, we have three correspondences labeled as U1, U2, and U3. According to the rigid transformation property, the lengths are preserved. Therefore, for U1 and U2, if the absolute difference between the lengths of A1, B1, and F1, B1 is smaller than epsilon, then these two vertices pass the compatibility test. On the other hand, for U1 and U3, they do not pass the test, and as a result, there is no edge between the vertices represented by these two correspondences. However, the maximum clique Inlier selection strategy does not always yield satisfactory results. We can attribute this to two main reasons. Firstly, we need an appropriate epsilon value to construct the compatibility graph, otherwise, the computed maximum clique may be incorrect. As shown in the figure, we provide an example of laser scan and BM map registration, where a slightly smaller or larger epsilon value can lead to an erroneous maximum clique solution. There are two aspects contributing to this issue. On one hand, the matching relationships are often based on keypoint and descriptor correspondences, but due to partial observations and the sparsity of point clouds, their errors are difficult to model accurately. On the other hand, the scene may contain some adversarial outliers. For instance, in this example of registering cylindrical objects, their arrangement is very similar, which can pose challenges in outlier removal. The second concern regarding this strategy is its computational complexity. If we have n correspondences, we would need to perform the compatibility test for all possible combinations, n, 2 times. In some algorithms, especially when the descriptors of keypoint correspondences are missing or weak, an all-to-all matching strategy may be employed, resulting in even more correspondences to consider. This further increases the computational burden. In response to these concerns, we propose a distrust and verify scheme. Firstly, we generate fewer but more accurate correspondences using point cloud semantic information. Then, instead of relying on a single epsilon value, we introduce multiple compatibility graphs by distrusting epsilon. We use a cascaded max solver to find the maximum cliques in each graph. Each maximum clique provides a transformation candidate through GNC. Finally, we perform geometric verification using the original point cloud information to identify the optimal candidate. By incorporating point cloud semantics, generating fewer correspondences, and leveraging cascaded max solvers with multiple compatibility graphs, our approach aims to improve the accuracy and efficiency of the registration process. The geometric verification step further enhances the reliability of the selected transformation candidate. For outdoor semantic matching, we took inspiration from the work called Segregator presented at ICRA 2023. We used the center points of trucks and cars for matching. As for other semantics such as buildings and vegetation, we employed FPFH descriptors to establish the matching relationships. In indoor scenes, where we only need to solve for 2D poses, we adopted a different approach. We focused on extracting cylindrical objects and used only the x and y coordinates of their center points for matching purposes. This simplification allows us to effectively handle indoor environments and achieve accurate 2D pose estimation. To obtain putative correspondences, we generate different compatibility graphs by setting different epsilon values. In this process, we draw inspiration from Clipper, which solves the maximum clique problem at each layer. The maximum clique is essentially a discrete optimization problem, and Clipper relaxes it into a constrained continuous optimization problem. It utilizes the projected subgradient ascent algorithm to solve this problem. In our algorithm, we start with a sparse graph. We have observed that the maximum cliques of this sparse graph are likely to be included in the maximum cliques of the next graph. Therefore, instead of independently solving each graph, we use the results from the previous iteration as the initial values for the next iteration. This approach accelerates the solving process, as it avoids starting from scratch for each graph and takes advantage of the previous solution. Considering that the semantic key points used for registration lose a significant amount of geometric information, aligning them does not represent the alignment of the entire point cloud. Therefore, using the original point cloud for set validation is our final step. We evaluate the alignment quality of the 2-point clouds by employing a truncated nearest point distance function. This helps us identify the pose candidate with the highest quality alignment of the point clouds. Our experiments are divided into 2 scenarios, indoor and outdoor. In the indoor setting, we collected 5 sequences and performed relocalization within a BAM map. The left image demonstrates typical scenes and trajectories from the sequences. We consider registration successful when the translation error is less than 1 meter and the rotation error is less than 3 degrees. The upper right image illustrates the distribution of optimal thresholds. It's evident that no single threshold can guarantee successful registration for all cases. The lower right image presents the success rates of our registration method compared to state-of-the-art (SOTA) approaches. For outdoor scenarios, we utilize the Kitty dataset. We selected registration frames from loop closures with translations ranging from 10 to 15 meters. Registration was considered successful when the translation error was less than 2 meters and the rotation error was less than 5 degrees. The upper right image presents the success rates of our registration method compared to state-of-the-art (SOTA) approaches in outdoor scenes. In addition, we conducted an ablation experiment on the compatibility test threshold. The table in the lower right corner illustrates that adding an additional threshold or having multiple pose candidates improves the overall robustness of the registration process. Thank you for watching our presentation. We appreciate your time and attention.